Hello there, this is Ms. Page, and this lesson is in our Unit 6 on using vertex form in different types of problem solving. In this lesson, we are going to look at quadratic functions in context that are in vertex form, and then solving problems with that vertex form. So we've seen problems similar to this before, but we've learned some new skills that we will be applying in these problems. So here it says that we are to solve and round to the nearest hundredth if necessary. So that tells us, all right, we're looking at using a calculator. And one of the things is you want to make sure that you can accurately use your calculator in these problems. So always make sure you're testing to make sure you can get the right answers here. So here we're looking at a situation we've seen before, or similar ones before. A rock is knocked off a cliff into a river. So when motion like that happens, it's modeled with a quadratic function, and here's our vertex form of our function. This is our a, this is our x minus h quantity squared, this is our plus k, and it models the height of the rock. Remember, function is referring to the y value. So this is saying our y, or our h of t, models the height of the rock, and that is going to be measured in feet. And then our t is like our x. That's our independent variable after t seconds. All right. First question says, when will the rock hit the surface of the water? So here we have to realize our when is talking about a time, that we're solving for a time. And remember that if we have two variables and we want to solve for one of them, we need to be able to determine a number to use for the other variable. And the number we have to figure out here is from the concept of the rock hitting the surface of the water. So we have to realize if we're solving for t, that means we need a number to use for h of t. And h of t is our height. And if the rock hits the surface of the water, that means its height would be considered 0 feet. So now we can set up our problem by substituting in 0 for our h of t. So we get 0 equals negative 16. Trying to get that out of there. There we go. 0 equals negative 16t squared plus 40. So now we are going to solve this problem. And so looking at its structure, we don't have a linear term. There's no t term with our t squared term. So that means we can use our square root property. So I'm going to add 16t squared to both sides to get t squared on one side. Now before I do my square root, I want to divide both sides by 16, remember? So I divide by 16. That's going to give me t squared equals 40 divided by 16. There's no need to reduce here because we're going to be using a calculator here in a moment. And so I would take the square root of t squared. Remember, that would create plus or minus, positive or negative of the square root of 40 divided by 16. Now, if 40 divided by 16 is a nice terminating decimal, you can use that decimal. If it's not, if it's a repeating decimal, or it's too long to be able to do the whole thing, then it's better to use the fraction. Now 40 divided by 16 is actually 2.5. So you could also look at this as positive or negative of the square root of 2.5. So when we use our calculator on the square root of 2.5, we get either it's approximately a negative 1.58 or a positive 1.58. Now these are, remember, both t values, and t is our time in seconds, so they are both supposed to represent a seconds quantity. So now we determine whether one or both, or maybe neither, makes sense in terms of the context. So for time, we know negatives don't make any sense, positives do. So this is going to be what we base our conclusion off of. So for our conclusion, the question was, when will the rock hit the surface of the water? Make sure you don't change the context to ground or something else. So the rock will hit the surface of the water. There's our context. You can say at, or you can say after, which is what I'm going to say. And then again, rounded values. We've talked about the importance in our writing to indicate that with the word about. After about 1.58 seconds. All right, so that finishes up that type of problem. So now the second part. Same function, same model, different question. What is the rock's maximum height? When does the rock reach this height? So again, when it talks about maximum, we should realize it's talking about a vertex situation in a quadratic function. So our function here of h of t equals, remember it's our vertex form. This means negative 16 times t minus 0 quantity squared plus 40. So our vertex is going to be 0, 40. And 0, this is our t value, so this is our time in seconds. And 40 is our height value, so this is our height in feet. And it's actually our max height because it's the vertex. So that's all we need. And we can answer the question. So the rock reaches, I'm putting them both together into one sentence here, so I'm kind of wording it to be able to do that so my sentence makes sense. So the rock reaches a maximum height of 40 feet. There was no rounding there, so we don't need about. At or after, actually, at 0 seconds is better because no time has passed, so after doesn't really make sense. So at 0 seconds. Now, this is the time in context. It would also actually be the moment the rock is knocked off a cliff. So you could interpret 0 seconds in terms of context that way too, and that would be a good type of conclusion. So the rock is at a maximum height of 40 feet when it's actually knocked off the cliff. All right, let's see what we've got next. So our part C with this model is when will the rock reach a maximum height, or sorry, not maximum, just a height of 10 feet. So again, we have to realize when in this sentence or this question is indicating we're looking for a time, which means we need a value for our height, h of t, and that height is 10 feet. So that understanding of this statement right here allows us to now take our function and replace our h of t with 10. So we get 10 equals negative 16 t squared plus 40. And now we're going to solve this equation. So I am going to actually add my 16t squared because I like positives better. You probably realize that about me by now. And I'm going to subtract 10 from both sides. So here I'm going to have 16t squared equals 30. Now before I do my square root, got to divide by that 16. So I'm going to divide both sides by 16. And now I've got t squared equals 30 divided by 16. Now I can take my square root. Again, if 30 divided by 16 is a nice terminating decimal, you can use the decimal. If it's not, use the fraction of 30 over 16, but there's no reason to reduce because we're going to be using a calculator. And so we have the square root of t squared equals positive or negative of the square root, and 30 divided by 16 is a nice decimal. It's a little long, but you can use it if you want to, 1.875. Don't round this, use exactly what it is. And then your t values are about negative 1.37 and positive 1.37. So again, each of these are t's, so they're each a seconds. So once again, a negative time doesn't make sense. So we base our conclusion off of our positive 1.37. So our conclusion, when will the rock reach a height of 10 feet? So the rock will reach a height of 10 feet after or at or in about, because we rounded, 1.37 seconds. All right. Last part for this particular model. Now we're going to take a look at the next example, which is a different model. Okay, so in this second example, we are looking at a model. So it says the height in feet of a baseball that's hit toward left field is modeled by this function. So again, remember the word function is talking about the function notation, the y values. So these y values model the height in feet of this baseball. So our function, again, vertex form, and x here is defined as the horizontal distance traveled also in feet. And we've seen problems like this before. But again, we're going to apply some new skills that we've been learning towards solving some problems here. So here's what is the baseball's height when it is hit. All right, so here in context, we're looking for height, which means, again, if we're looking for height, our height equals what? Or our h of t equals what? Then we have to have a number for t before we can do that. So that means we have to interpret in context the time when it is hit. So we have to realize the time quantity when the baseball is hit would be understood to be, in terms of how x is defined, horizontal distance traveled, 0 feet traveled, because it hasn't moved anywhere yet. So that's our t, or actually not t, sorry, we're looking at x. Oops. X, our x is defined as 0 feet traveled in this context. When it is hit is actually x, 0 feet traveled. Sorry about that. So that means here, this is also supposed to be x. And so we're looking at h of 0. So we know what that means. That means that we are going to substitute in 0 for our x variables, which we only have the one. So we have negative 0.05. Goodness. So 0 minus 25 quantity squared plus 35. So here we have to make sure we do our order of operations. So we do our subtraction inside our parentheses first. That's going to give us negative 25 squared. You can do this all at once actually in your calculator. Just type in negative 0.05, put parentheses around your negative 25, then square it, and then do plus 35. If you want to do it piece by piece, you can. You'd get a positive, remember, here of 625. Then multiply those and add. And what you're going to get is, at the end, 3.75. No rounding is actually needed. You'll notice if you do the math on your own. So this is my h value, remember, my height. So in conclusion here, what is the baseball's height when it is hit? So when the baseball is hit, its height is 3.75 feet. All right. So next part, part B here. So in part B, it says, maximum height. What is the maximum height the baseball will reach? When does it reach this height? So again, we are looking at a vertex problem because we're looking for a maximum. So our vertex here would be 25, 35. Now, it's real important we interpret our variables here in terms of our context. Like I accidentally was using t over here. It's not a t, it's not a time this time. So remember, this is our h and this is our x in this case. So this is our height in feet, the 35. And the 25 is the feet of distance traveled. So we have to make sure that we get that into our context. So the baseball will reach a maximum height of 35 feet after traveling, or when it has traveled, 25 feet in distance. All right, that finishes up part B. Let's take a look now at part C. Same model. So here, how far will the ball have traveled horizontally? We have to realize traveled horizontally, remember, is how our x variable is defined, horizontal distance. So that means we're looking for an x. And if we're looking for an x, we need a value for our h, or h of x. We need a number, and that's supposed to be a height, so we're looking for a height. So it says when it is 8 feet above the ground. So above the ground would be a height context. So that means that our h of x will be the number 8. So that allows us to set up this problem. So we get 8 equals negative 0.05 times, in parentheses, x minus 25 quantity squared plus 35. So now we're going to use some new skills here that we've learned to solve for x here. So again, I want to isolate the x minus 25 quantity squared. I used to use my undoing algebra. So I have to undo the addition first, subtracting 35 from both sides. And that is going to give me negative 27. Then I have to undo that multiplication. So I divide both sides by the negative 0.05. Again, if this turns out to be a nice number, terminating decimal or integer, use it. If it doesn't, then make it a positive, because negative divided by negative is positive, and just use the fraction so that you get the most accurate answer. In this case, though, it's a very nice number, positive 540. So we'll use that. So now we've got our quantity squared isolated, so we are now ready to take our square root. Remember, we're going to get a plus or minus over here in front of the square root of 540. So our square and square root cancel over here. This will be x minus 25. Over here we still have positive and negative, square root of 540. Then we're going to undo the subtraction and add 25 to both sides. And this part's going to become 25 plus the square root of 540, and separately 25 minus the square root of 540. And each of those is equal to an x value. So now we use our calculator on both and then interpret and see if they make sense. So the 25 plus the square root of 540, this is about 48.24. And the 25 minus the square root of 540 is about 1.76. So these are both positive quantities, and x is defined as a horizontal distance. So both positive quantities make sense in terms of the context. So what you have to realize is it also makes sense that there could be two answers like we are getting here, because remember, this baseball was hit up into the air, and we're looking at where it's at 8 feet above the ground. And so it's saying it's 8 feet above the ground twice, because its maximum is somewhere between them. And so it's hitting 8 feet above the ground, a height of 8 feet on the way up, and again on the way down. So our conclusion here is, so the question was, how far will the ball have traveled horizontally when it is 8 feet above the ground? So it's actually got two distances. We want to do the shorter distance first because that's the one it reaches first. So we will say the ball will have traveled about 1.76 feet and about 48.24 feet horizontally when it is 8 feet above the ground. And there we go. All right, I think we have one more to talk about. Part D. So part D says, how far has the ball traveled? So again, traveled is a horizontal distance and x description. So we are once again looking for an x value. So that means we need a number for h of x. So it says when it hits the ground. So h is our height. So if the ball has hit the ground, we know its height is measured as 0, and in this case 0 feet. All right, so now that allows us to set up our problem. So we're now going to get 0 equals negative 0.05 times x minus 25 quantity squared plus 35. So now we begin the solving process. So again, we want to, before we take our square root, we need to get this x minus 25 quantity squared by itself. So we're using our undoing algebra. We're going to undo addition first and subtract our 35. Zero minus 35 is negative 35. Equals this. So then our next step is going to be to undo the multiplication and divide both sides by the negative 0.05. So once again, if this division over here is a nice number, terminating decimal, integer, then use it. If it's not, then make it positive because a negative divided by negative is a positive, and use the fraction. This part over here becomes our x minus 25 quantity squared. And turns out when you divide these numbers, we get a nice number of positive 700. So we'll use that. So now we can take the square root of both sides. Remember, that's going to give us a positive or negative in front of our square root of 700. We have the square root of our quantity squared. So over here, our square and square root undo each other, and that gives us x minus 25. We still have positive or negative square root of 700 over here. So now, that one was too high. We are going to add 25 to both sides. So this is going to give us here, put this out of the way. So now we have, these will both be our x's, so we get x equals 25 plus the square root of 700, and separately x equals 25 minus the square root of 700. So we calculate them both separately on our calculator. And the 25 plus the square root of 700 to the nearest hundredth is about 51.46. And x, remember, is horizontal distance measured in feet. And 25 minus the square root of 700 is about negative 1.46 feet. So this would be a horizontal distance traveled. So a negative distance might be interpreted as going backwards, but our baseball can't go backwards and forwards. So in this context, the negative doesn't make any sense. So we have only one value here. And again, that is how far the ball traveled when it hits the ground. So the ball traveled about, travel doesn't have two L's, so let me fix that. I don't like to misspell things. The ball traveled about 51.46 feet when it hit the ground. Or you could say before it hit the ground. I like that too. All right, so that finishes up all of the example problems that I wanted to make sure we talked about. So from here, you should have enough information to do the assignment. All right. Signing off. You guys have a good day.